like it, you miss something, you kind of think that you can skip and come back, well, you can. It's going to be online in Canvas. The terms of art you may be hearing from some of your other instructors for this distance learning, this online stuff, it's called synchronous when we all meet together like we are now. Okay, because we're all synchronized together, we're meeting in the same place on the same website. And then there's asynchronous. I think that works well in a lot of humanities classes where stuff is left for you, you pull it up at your leisure and you respond to it. We're a little bit of a mix. You know, I saw that everybody pretty much did the pre-assignment reading and the reading quiz, so that's good. Of course, there's going to be a worksheet. If you haven't downloaded it, at least have it available, and I'll show you where that all is. Maybe I should take a second just to do that right now. I'm currently sharing. I'm going to stop the share here, and I am going to, let's see, share screen with you. And the button pushing will get better for me over time. That's my promise. Share screen. I'm going to share. Where are we? Is that? Yeah, there it is. Okay, and you should recognize this as Canvas. At least this is what it looks like from my end. And so if you're looking, it does give you all the due dates. So it's an important resource to stay on top of. Pretty much before spring break, most people turned in worksheet 17. So if you notice here, I got worksheet 17, the assignment right there, which tells you the due date, how many points it's worth. And then once everybody's turned it in, I post the solutions. So there's worksheet 17 solutions. The things we're going to be working on tomorrow, okay, that's the capacitors worksheet that we had before spring break. There's the assignment itself. And of course, due today is the mastering assignment for chapter 26 on capacity. Bless you, if you scroll up to, if you scroll up to current and Ohm's law, or actually down, you can see all the material. I usually put my PowerPoints, my notes right up at the top. Indented one level, if you're looking for a pattern here, is the assignments, and those are the pre-lecture assignments. And so today was A, and so most people did this one that I'm hopefully pointing at, and hopefully you can see as I'm sharing the screen with you. Okay, I'll put this away right here. And I guess the if you scroll down, you can see worksheet 19 and 20, which were passed out before spring break. The one for today is worksheet 21. So if you just click on that, you can look at it. Takes a second. They're PDFs, and that's going to be the worksheet for today. It's just one page. All right. So are there any questions before I move on? You can unmute yourself, I think, and if you got any questions, but that's where you'll find the material. And that's what we're gonna be doing. We're, as much as possible, pretend we're still in class. It's just our meeting will be virtually via the Zoom site. If something happens to it, there are a number of backups. So we'll continue on as best we can. If there's ever an issue where connectivity is lost, either my my Xfinity Wi-Fi or on your end, I am recording, as I said. I'll be posting it on the Canvas, and you can see, hopefully, I created a module called lecture videos, and actually today and Wednesday's lecture are sitting right there. I recorded it last night, so I've kind of practiced this once, and it's available if you need to go back because something I say during class you've missed. All right, last chance for questions, because then I'm going to move on. Yep, go ahead.
Can you hear me? How are labs going to go for the rest of the semester?
Good question. I got to be creative on that. That's the hardest part, isn't it? Next week, I'm going to create a video for you in my basement. Some people call it a man cave. It's got a pool table, all that kind of stuff down there. But I took home a lot of stuff from Washington College. Dr. Kem said, hey, yeah, nobody's using it for the rest of the semester. So I have some of the lab materials, at least one set of apparatus for the next 3 labs. Starting next week, I'm going to videotape me doing the lab. And then I'm going to create either FET assignments or homework assignments that you're going to complete and turn in. And so I think it's going to be, obviously the problem is you can't put your hands on the equipment, but you can watch me do it. And then if you look next week for the simple circuits, what we're going to be talking about today, there's a nice FET assignment already in mastering that pretty much mimics everything you would have done in the lab. And to the best I can, that's what we're going to do. I only expect we're going to have 4 more labs. Okay, there are going to be 2 on these circuit things, resistors and capacitors. We're going to have a Faraday's law lab, and then the last one will be diffraction and interference. We're going to be talking about physical optics at that point, and so we'll be talking about that. And a lot of them are going to be simulation based. So those FETs we've been working with, that'll be a lot of what's going on. So that's a good question. Other questions on anything, labs, policies? I hope grading policies continue exactly the same. The issue, of course, is that you have to upload your worksheet just like you've been uploading labs for the entire semester, but now you're gonna have to do that for every worksheet. The mastering stuff exactly should stay the same as it always has, okay?
How are we gonna do tests?
Test is going to be a take home, obviously. I can't have you all meet up anywhere. And I expect the second midterm and the final exam will both be done on mastering. Okay. I'm not going to make it closed book. I'm going to make it open book. I'm trying to decide if then I still need to do an equation sheet for you, because I had one started, obviously, that you use for the first midterm, but that's how the exam is going to be. Okay. And if there is, I'm not going to make them time limited. So anybody who has something from OAS that gives them extra time on an exam or a quiet place, obviously the person who has to get the extra time at a quiet place is you. I'm going to make them open book in mastering, unlimited time. Fair enough?
Would we still get?
Pardon?
Would we still get partial credit for work if it's in mastering?
You know, that's a hard thing, and I'm going to design labs where there's some partial credit, but you remember how on the multiple choice section of midterm one, there was a little bit of partial credit if I saw something. I mean, I'm still playing with the format. I may have you do one or two problems where there is partial credit, but you know that takes time for both you and me. The problem with no partial credit, you know what we do as faculty to compensate for that? There's a curve on the exam. Yeah, people who talk about putting curves on the exam often have to do that because they don't award partial credit, and so then your average score is somewhere in the 60% range, and you know no partial credit's awarded, and so you just shift that up to where you want the average score to be, and that's what people have been doing. We did that at the Naval Academy for all our final exams. No partial credit, but then the exam was graded, as people say, on the curve. We looked at the distribution and we adjusted it to account for the lack of being able to award partial credit. Great questions. Anything else? All right, well, let's start for the material of the day, I guess. I got to find I hate this Mac, and eventually I'm going to take charge of it and have it do things my way here. Where is there it is. So I think if I come out, is it screen? Yeah, it's screen sharing over there. I'm going to do a new share, which means I stop this. I'm going to go back to my iPhone, sharing that via AirPlay. All right, stop share. All right, and where does it put it then? Okay, and then I got to share screen and iPhone via AirPlay. And now it's going to make me do some things over here like screen mirroring. And we're good. And then I got to put that away. All right. And so where did I put my pen? There it is. The things I want to talk about, first of all, are a review of series and parallel. And, you know, wow, that's not good. I guess I got to be more careful. Series and parallel networks. And I apologize for my handwriting. It is what it is, I guess. Get that out of here now. And parallel. And remember, we'll go with capacitors for today because that's what we did before break. We have these things with batteries, right? And batteries have some voltage associated. We call that the electromotive force, and the symbol we give is E. It's a misnomer to call it a force. It's really an energy per charge, a voltage. And then we created circuits like this one, where I put two capacitors. Let's call this one C1 and this one C2, okay? And we call that a series arrangement, okay? And you can see you've connected the capacitors tail to head, I guess, or head to tail. And a couple things we believe about that. I believe that the charge, which leaves the battery, and I'll draw little dots charges, goes to C1, it pushes some charge off there, goes to C2, pushes charge, goes back to the battery. The charge is the same everywhere. And so as we're going to discuss today in a series circuit, the charge is the same. The rate at which charge moves, which we call current, is also the same. Okay, and so that's an important idea for series circuits. One thing I want to make sure you understand is absolutely false, but you see people do all the time, is the battery voltage, the electromotive force, that E thing there. Pretend it's a 9-volt battery, for example. There is not 9 volts across C1, and there is not 9 volts across C2. People use it in equations all the time. It's not true. What we do think is true, because we said earlier that if you take the sum of the voltages around any closed path, it has to be 0. And that's an important thing we're going to talk about today. So if I start where I put the X, call that 0 volts, because why not? I can put the 0 point anywhere I want. I increased by 9 volts to get to the other side of the battery. Okay, so that's a plus 9. I must lose some voltage across C1, lose some voltage across C2. If they're equal, it could be 4.5 volts, 4.5 volts each, and that adds up to the 9. And so it's plus 9 volts, minus 4.5, minus 4.5, and I'm back to 0. Okay, and so in the start of a problem, if they're different, you have no idea what the voltage is across C1 and C2. And that's the deal. But we'll be talking about the sum of the voltages around the closed loop being equal to 0. We did say for series capacitors, if you do have to get an equivalent and you need to combine them, the equivalent capacitor adds as a reciprocal 1 over C1 plus 1 over C2 is how I would get a single capacitor to replace those two. All right, so we're rolling along here. Let's draw a parallel circuit now. And it looks more like, I call it a ladder arrangement. Okay, same battery with the same electromotive force. Maybe it's a 9-volt battery. We'll call this C1 still, but I've kind of moved where I put it. And I've moved C2 a little bit with some different wires. And this is a parallel arrangement. And if charge or current is the same everywhere in a series circuit, what's the same for the two capacitors and the battery in a parallel circuit? And the answer is voltage, the other thing. So voltage is the same. I don't know why I'm writing it out this time. I just wrote V on the other side, is the same. Okay, and so that's the important thing about parallel circuits. By the way, if I'm looking for an equivalent capacitance here, we said it's the sum of the two capacitors is the equivalent. If I get too close to the edge here, it starts to not write. Okay, there it is. That's the equivalent capacitance if I wanted to replace those two capacitors with a single one. Okay, so that's what I would get. And the thing that's kind of interesting is if I get to this point right here, okay, up at the top there, there's some charge which left the battery. And when it gets to that point, it has to split, and some of it goes to C1 and some of it goes to C2, right? And so what we believe here, I'm going to call this the charge leaving the battery. And this is the charge going to capacitor 1, and this is the charge going to capacitor 2, okay? I think we believe that we have conservation of charge still, that nothing gets destroyed or created or diverted out of the circuit. The charge leaving the battery is equal to the charge going to capacitor 1 plus the charge going to capacitor 2. And in a little bit, I'm going to say, hey, if I look at the rate of change of charge, that must mean that the current leaving the battery is equal to the current going to capacitor 1 plus the current going to capacitor 2. We don't worry about that much with capacitors because it doesn't take long to get them fully charged, at which point there's no more current, there's no more motion of charge. So, but it will be true here shortly. Okay, and so that's just a quick review with my poor handwriting on this whiteboard here of series and parallel. Any questions about that? Because if not, I'm going to go on to do a problem. And it's the problem 3, I guess, from worksheet 17 that most of you turned in. I think everybody's now turned in because I got the solutions posted before spring break. Questions? Everybody still going good out there? All right, so if you remember this particular problem, there was a 10-volt battery here. And I don't know why I'm drawing it like that, just because that's kind of the way it was on the worksheet. I'll make it a battery when I redraw. And then there were 3 capacitors arranged like this. And I'm not going to give them, well, maybe I should give them numbers. I'll call this one, I guess, that's not good. There's my eraser. If I let my hand touch the screen in any way, it's a pen tablet. So that's what happens, okay? And why you shifted over to black there, I don't know, it touched a pen. All right, so we'll call this one C1 right here, this one C2, and this one C3, just for lack of better names. And C1 was equal to 0.3 microfarads. Remember, a micro is 10 to the minus 6th farads, capacitor C2 here is 1 microfarad. Make sure that dot's visible for you. And C3 is equal to 0.25 microfarads. Okay, and the first thing you want to do with a circuit like this is redraw it, and you can see that C2 and C3 here, aren't they in parallel? And so can't I replace them with a single capacitor? I'm going to draw the 10-volt battery like it probably ought to be drawn in the worksheet. Okay, and so I got C1 right here. That's the 0.3 microfarad capacitor, and then we said for two capacitors in parallel, all we do is we add C2 and C3. I dropped a 5, didn't I? I said it, but then I didn't write it. 0.25. And so if I combine those two in parallel, okay, I get 1.25 microfarads just by adding them. I'm not going to show that work. Hopefully we can all do that in our head. 1.25 microfarads. That's the total capacitance that represents C2 and C3. Everybody with me so far? Good. And now I got two capacitors there in series with each other. And I guess I need to figure out an equivalent capacitance that replaces those two. And I'm going to call that C equivalent. Okay, it's pretty terrible artwork, but I think you're hopefully following me. And so we said that 1 over C equivalent is equal to 1 over, let's see, 0.3 microfarads plus 1 over 1.25 microfarads. And I went to my calculator. I just got to warn you, when you do this, you're going to take the reciprocal of 0.3. You're going to take the reciprocal of 1.25. You're going to add those two up. When you're done adding them, you're not done yet. You got to take the reciprocal of that result. And if you do that correctly in your calculator, you get the equivalent capacitance is 0.242 microfarads. Okay? And that's good. And why did I go through all that trouble? Why did I need to create this circuit up here? And the answer is the capacitance equation that relates the charge on the capacitor, the battery EMF, or the voltage across the capacitor, which are equal because they're in parallel, aren't they? Okay, is that the charge is equal to C times V. So if I'm trying to figure out what I've called the charge leaving the battery, the charge that comes on here, I need to know the voltage across the capacitor, which is 10 volts. I need to know this equivalent capacitance right there, okay? And then I can figure out the charge leaving the battery. That doesn't work on either of the other two circuits I have here, because the only circuit that I can make use of the 10 volts that I have is this very last one I drew, okay? And so I can say the charge, which I'm gonna say is leaving the battery, right, is equal to 0.242 microfarads times the voltage, which is across it, the 10 volts from the battery. And I don't know why I wrote E this time, other than that's what we've been calling it, but it is 10 volts right there, okay? And C equivalent, of course, is what I calculated in the final step. That's the charge leaving the battery, okay? Now, step back a second. That's the charge leaving the battery right here. So the question is, of course, what is the charge on capacitor 1? Well, the charge on the capacitor 1 being in series with the battery has to be the same as the charge leaving the battery. And so I didn't finish my math here, but 2.242 times 10 is 2.42. The micro stays 10 to the minus 6, and a farad times a volt is, of course, a coulomb. So that's actually the charge on capacitor 1, okay? Q1, the first one, the 0.3 microfarad capacitance. A lot of people made a mistake right here. When they went Q is equal to CV, they put in 0.3 microfarads instead of 0.242 and multiplied it by 10 volts. The reason that's wrong, of course, is what we said before. There is not 10 volts across the 0.3 microfarad capacitor. It's not true. In fact, let's figure out from this middle circuit that I drew here, the one with the two series, what is the voltage across capacitor 1? Well, the voltage across capacitor 1 is the charge on capacitor 1, which I just figured out was 2.42 microcoulombs. And if I divide it by the capacitance of 1. That should tell me what the voltage is, what the potential difference is across capacitor 1. And so it's 2.42 microcoulombs divided by the capacitance of capacitor 1, 0.3 that's a lousy looking 3. That's even worse, but that's what I got. Microfarads. Notice the micro and the micro cancel. A coulomb divided by a farad is a volt. And so when I do this math, 2.5 divided by 3, that's going to be a fairly big number. It turns out to be almost 8.1, 8.06 volts is the potential difference across that capacitor. Okay, just about 8 volts, a little over it. Okay, now what we said before about the voltage around a closed loop being 0, if I got 10 volts from the battery and there's 8 volts across the capacitor, what must be left at the 1.25 microfarad capacitor? Well, just using one digit, 10 minus 8, that leaves 2 volts right here. Okay, let's see what it turns out to be using the same idea. If I want to find the voltage, I don't have a name for that guy. It's not 2, it's not 3. I'll call it the parallel. Oh, go away. I'll call it the parallel combination. Yeah, I'm too close to the pens down here, so I'm gonna have to get rid of that, I guess. Okay, do it somewhere else. Okay, so the voltage across the parallel combination. Now, it's in series with the 0.3 microfarad capacitor in this circuit, right? So that 2.42 microcoulomb number is also the charge across it. So if I go Q on the parallel, that's a Q parallel, Q sub P, and I divide by the capacitance of the parallel combination, the 1.25, let's see what I get. And it's 2.42 microcoulombs divided by 1.25 microfarads. Coulomb divided by a farad. Micros cancel. And let's see if there's room here. Not room. Let me get rid of something right here. I'll get rid of V1 here and move it, as this was equal to V1. So this guy right here is going to be equal to, when I did that, I got 1.94 volts. And if you look, if I add the 1.94 volts up to the 8.06, don't I get to 10 volts across my battery? And the answer is yes, I do. So that makes me feel good. I know what the voltage is across the 1.25 microfarad capacitor, which admittedly is fictitious. It doesn't exist. It actually is the two capacitors, C2 and C3. All right, I'm going to erase this mess a little bit, okay, to leave myself some room. And I'm going to keep those two numbers because those are big numbers, what the voltage is across the 0.3 microfarad capacitor and what the voltage is across the 1.25 microfarad capacitor. So I'm going to keep those numbers here because we're going to need them. Go away, go away, go away, erase the board. Because the last question is how much charge is on C1 and C2, okay? And so let's see, this was the voltage parallel was, I'll make it look a little neater. 1.94 volts and across, and that's the parallel combination, which is C2 and C3, which of course begs the question, what is the potential across both C2 and C3? They're in parallel. They're the same because parallel voltages are the same. That's a rule. And so I guess if I'm looking for the charge on Q2, okay, Q2 is 1 microfarad, 1 microfarad. Now let's write the equation out for you. It's the capacitance of 2 times the voltage across 2, which I just said is 1.94 volts, okay? Volts, why'd I put parallel there? I don't know, I don't need that. All right, so 1 microfarad and 1.94 volts. I can do this math in my head, 1.94 volts, not microvolts. And that gets me 1.94 microcoulombs because a farad times a volt is a coulomb. And I just brought the micro, the 10 to the minus 6. If I'm doing the same thing with Q3, okay, I take C3 and I multiply it by voltage 3. Voltage 3 is also 1.94. They're in parallel. They have the same voltage. And so I go 0.25 microfarads times 1.94 volts. And when I did that, I got 0.484 microcoulombs. Now, remember, how much charge left the battery? If you were keeping track before, you remember that we said that the charge leaving the battery was 2.42 microcoulombs. Okay, that's how much charge left the battery. It all got deposited on C1. Then when you got to this point right here, the junction, the node that separated out the parallel part of the circuit, we said the charge should split. So the amount of charge that goes to C2 and the amount of charge that goes to C3 has to be adding up to the original charge which left the battery. Let's check and see if that's true. Is 1.94 microcoulombs and 0.48 microcoulombs. Does that add up to be, let's see, 2 carry the 1, 14, carry the 1, 2.42 microcoulombs when I add it up? So these two numbers check and are the same. And if you didn't get that, and a number of people didn't on worksheet 17, that's how you have to do the problem. Any questions on what I did there? Anybody bored out of their mind right now? Don't answer yes if it's true. All right. So let's see, I'm going to come out of this share mode here. And now it's time to talk about the material for today before I cut you loose and say, hey, let's work on where'd you put it? Up there, stopping that share. And I see you're still here physically, so that's good. Nobody's left yet. Let's take a look at sharing the PowerPoint, which, where is it? Where is it? Right there. And share. And let's come on, and oh, that's always in the way, which makes me nuts. All right, now I can get to it. It's your chance for questions, I guess, if taking a little break here. We want to talk about Kirchhoff's rules, and we've really summarized them a little bit. Are our pictures all in the way? I'll try to get that out of the way. If that bothers you, somebody pipe up and I'll try to move it as best I can. Is there a way to get rid of it?
We can't see your pictures. We can only see ours.
Okay, I'm at the top.
You have it on the screen doesn't matter for us.
Okay, so it doesn't matter? All right,
No.
good. All right, good. So I'm going to go back, and Kirchhoff's rules, sorry, I advanced the screens. Sometimes it advances the screens, are really the things we just talked about when we're talking about series and parallel combinations. Conservation of charge is what happened at that junction when a parallel circuit is created. There has to be a junction or a node, and then two elements come out of that, right? And so what we said is at any junction point, the sum of the currents entering the junction must equal the sum of the currents leaving the junction. That's equivalent to what we said, the sum of the charge entering the junction has to be equal to the charge leaving the junction, which deposits itself on each capacitor. Okay, and so that's referred to as Kirchhoff's junction rule. We've actually been using it all along. We just haven't formalized it and given it a name. It's named after a guy, Kirchhoff, who did work on electric circuits in the late 1800s. The other rule, which we said, was that the sum of the changes in potential around any closed path of a circuit must be zero. And we did say that, but when we said that earlier, we were thinking about like a point charge, and you move in space outside a point charge. And if you start at one point and you move a charge all the way around a loop and you come right back to where you started, well, we said electric fields are conservative. And because they're conservative, the net work is done as zero. There's no change in work. There's no change in potential. And so we said, as long as you come back to where you start, you've done no work, and no change in potential energy, no change in electric potential, which is just potential energy divided by charge. And so we can do that with circuits. And I've alluded to it, but I haven't been very formal in the way I'm doing it. And so I think that's what'll be the change here today for you, is we're formalizing some rules. And so here's an example circuit. You should recognize it as a series circuit, only this time the series circuit is two resistors instead of two instead of two capacitors like we did in the problem previously, and we've been talking about, because we talked about resistors right before break. We know a law that relates the current through the resistor, the value of the resistance, and you can see these two are 400 ohms and 290 ohms, right? 400 ohms, 290 ohms. And the battery voltage in this case is a 12-volt battery. And there's the positive side of the battery, and you can see currents drawn as going around. And if you start at point A and you're on the positive side of a 12-volt battery, it's kind of reasonable to say at point A, your potential is 12 volts. Okay, and so then right here at this little place where the voltage starts going down is where you're going across the resistor over to point B. And we'll be able to show this with a calculation later. But if current is going to go from A to B, the potential at A has to be higher than the potential at B, and then positive charge will move from higher potential to lower potential. It turns out it's about 6.8 volts if you figure it out for this circuit. But I haven't given you all the rules yet to make that measurement, or make that calculation, but we can, and it has to fall. And this gets me to point B right here. Okay, and then if the current is going to go on to point C, C must be at a lower potential. We'll just declare the potential at both C and D to be 0. Okay, oftentimes, and I have an annotate button here. Oops, that isn't what I wanted. There it is, annotate. To make it clear that there is 0 volts at a particular place, you'll see a lot of engineers, electrical engineers, draw a symbol that looks like that, and that's ground. And so we're saying, I'm making that point 0 volts. But remember, potential energy can have a 0 point anywhere you want to put it, because it's always the change in the potential energy that matters. Electric potential is exactly the same. It's the change in the electric potential that matters. So if I'm at 0 volts here, I go across a battery, which has a 12 volt increase. Over at point E right here, there must be 12 volts, right? And that's how this works. And then if I dropped 6.8 right here, it drops to 5.2 volts and then back to 0. And we don't put this in most of our circuits. Occasionally I will, but that's called a ground. And that just ensures that at this point right before the battery, we really want to make it 0 volts. And if you talk about like the grounding plug on an appliance of some sort, that's what they're doing. It's generally literally going to a stake someplace, maybe at your house, which is plugged, pounded into the ground, and that's what we have. This little mechanical model here is just one resistor, and the electrons obviously, are going the other way. We'll talk about positive charge. We'll pretend these little yellow balls are positive charge. An atom without an electron is what we talked about before the break, and it comes down the hill here, just like the charge, the current is moving down that hill right there. Okay, it rolls around, and then something has to lift the ball, the positive charge, back up to the top of this hill here. And of course, that's the battery. The battery is the elevator that brings the ball back up here, and so it can go around the circuit over and over and over again. All right, and we talked about the rates of that. We talked about current, how you can calculate current from the movement of the charge and the speed of the moving charge before the break. Let's keep moving on here. Come on. Oh, I gotta do something. I gotta clear my drawings, and then I got to put that away, and then I can advance to the next slide. Okay, and so here is a simple series circuit again, just like the one I drew before, only I don't like that this is here, so I'm going to move it somewhere else, like down there perhaps, and I'm going to apply the Kirchhoff loop rule in a very formal sort of way. Back. There's my annotate button again, so I can draw. Okay, and I'm going to start right there, as I talked about, and that's going to be 0 volts. And the very first thing I'm going to do is I'm going to go to point A. And if you think about it, C everywhere here is in series, so the voltage in series is the same. So every place from point C all the way down to my X, even right into the negative side of the battery, that's all 0 volts. But I go to the positive side, so I've increased my potential from 0 up to the voltage across the battery. If you want to call that electromotive force, in some applications it can be. It could be a 9-volt battery, it could be a 12-volt battery. Okay, I get up to here, and now I'm subtracting off the voltage across that resistor because this side has a higher voltage than that side. That's what makes the current move in that direction. Okay, and so I subtracted off the voltage from A to B, which is the voltage across resistor 1. And then on this resistor, that must be the higher potential side if the current is still going to flow from left to right, from B to C. And so I have to subtract off that voltage. And of course, I'm back to where I started right here. I'm at my X. So the sum of the voltages around that loop has to be 0. Now, the first obvious math step to do is the voltage AC. And by the way, I'm writing with my mouse here, so penmanship is bad, must be the voltage across resistor 1, which I called AB, plus the voltage across resistor 2, which I called BC because of the way I labeled these points up here. Okay. Now, remember, what is the voltage across resistors 1 or 2? Either one of them, their voltage is given by Ohm's law, which is the voltage across an element is the current going through the element multiplied by the resistance of the element, in this case, resistors, okay? So that means that the voltage AB across resistor 1 is current times resistor 1, and the voltage across BC is current times resistor 2, okay? And we don't have numbers here for these things, but in principle, I might tell you it's 100 volts and it's 300 volts or whatever it was on the previous slide. Now, one thing you noticed is I did not subscript the two currents as current 1 and current 2. And you might go, well, why? And the answer is, of course, they're in series with each other. And so the current is the same. Since the current is the same, I'm able to factor it outside and I'm left with the sum of the two resistors in the series combination inside the parentheses. We refer to that as the equivalent resistance of this circuit right here. So these two resistors, 1 and 2, could be replaced by a single resistor whose value is the sum of R1 and R2. Now remember, for capacitors, slightly different rule, right? If I was taking two capacitors in series, I would have said 1 over the equivalent capacitance is 1 over C1 plus 1 over C2, right? That's how we started talking about our series capacitors at the start of this little session here today. Completely backwards, isn't it? Completely backwards. And we'll complete the backwardsness of this here in just a second. Any questions on what happens with a series circuit of resistors and how it's different from a series circuit of capacitors? Awesome. Awesome. All right, I got to erase that now. Clear drawings, and then the system will let me go on to my next page. I think no. All right, I got to put this someplace else now.
Can I ask a question?
Yeah, go ahead.
Oh, how do you, will like current be given to you, or would you have to like calculate?
You know, it's every problem's a little different. I'm going to tell you this. There's one equation right here, right? That the voltage is equal to the current times the sum of the resistors.
Mm-hmm.
Okay, one equation, I can, I would have to give you there's 4 things, right? The voltage, the current, and the 2 resistors. If I give you 3 out of the 4 of those things, you can calculate the other one, couldn't you?
Yeah.
Yeah, and that is going to be the math rule that we employ today, right? Because in a second here, I'm going to do a problem with a little more complicated circuit, and I'm going to give you the resistors and the battery voltage, and you're going to have to calculate the current. But there's going to be a couple currents. But it seems to me that I have to give you either enough equations or enough constants to let you calculate the unknown things. And if I can make you have 2 equations, well, there are 2 things that you might not know, right? 2 equations, you can solve for 2 unknowns. If there's 3 things that you don't know, you must have 3 equations that you're able to write like this one right here, okay? All right, so that a good question, and the answer is every problem will be a little different. Very often we ask you to find the current because that's what you really don't know. All right, how come it's not letting me advance? Let's try to advance. All right, we're locked up. Awesome. This thing's bugging me. Let's see. Oh, that's why I'm still in the annotate mode, and it will never let me annotate. There we go. Now I'm advancing. Yeah, there's some things with Zoom that are a little clunky, but so now I've drawn a parallel circuit. We'll work through them. Parallel circuit, and hopefully you can see the resistors are in parallel, just like the capacitors were parallel at the start of this little talk. I was a little more energetic this time. I drew a 3rd resistor. Okay, I'm going to cover the top up. At least for me, it's covered up. And I want to look at a junction now. I need to move that down because I need to see my annotate button again. All right, and then I can move that back up. And you'll notice there's some current leaving the battery. And when it gets to this point right here, I could have drawn that as one big dot, right? Because the current splits into 3 places right there, I1, I2, and I3. And according to what we call the junction rule, the current leaving the battery has to be equal to the current going to resistor 1, which I've labeled as current 1, the current going to resistor 2, which I've labeled as current 2, and the current going to resistor 3, which I've labeled as current 3. Okay, so a mathematical statement of Kirchhoff's junction rule in this case is that the current leaving the battery, which I've unsubscripted, I just called it I, right, has to be equal to the sum of I1, I2, and I3. And I'm hoping that's more than just something you memorize. I'm hoping that just makes sense. Okay, no charge is kind of flying off the circuit anywhere. Whatever leaves the battery has to go someplace, and it just has to split between the 3 possible places it can go in this circuit. Okay, and so I'm starting with the junction rule here, and of course Ohm's law still applies. Did I lose my cursor? Oh yeah, yep. This happened to me last night while I was practicing. Yes, I did. And so I got to move you guys. I got to come up here, and I got to come out of annotate, and maybe I'll get my cursor back. No, it doesn't look like. Yep, I got my cursor back. Good. Yeah, these are kind of clunky things with this Zoom thing. So now I got that back, and I can point to things again. Remember, Ohm's law is still the voltage is equal to I times R. This time I'm solving for the currents. So it's the voltage divided by the resistant is the particular current. I1 is the voltage divided by resistance 1. The voltage divided by resistance 2 is I2. And of course, voltage divided by resistance 3 is I3. And so I've made that substitution. Now, again, in this case, why didn't I subscript the voltages? And the answer is because what we said at the start, in a parallel network, any kind, whether it's resistors or capacitors, the voltage is the same. Okay, and so since it's the same, I can factor it out of this equation right here, leaving the sum of the resistors as reciprocals, and I can replace all 3 of these resistors right here with a single resistor, which we call the equivalent resistance. Apparently, the equivalent resistance is 1 over R1, 1 over R2, and 1 over R3. You might remember that's exactly the opposite. I need to move here so I can write again. Come on, give me my little, there it is, annotate button, okay. And I think if you remember, for capacitors in parallel, the equivalent capacitance was just the sum of C1 plus C2 plus C3, okay. So again, it's absolutely backwards. The rule for the equivalent circuit element for capacitors is compared to batteries, and it's just something you have to learn. Okay, good stuff. And I'm kind of done talking about the rules now. I think it's time to do a problem. Any questions on parallel circuits? And you can see how they're different from series circuits, and you can see how they're different from networks of capacitors, I'm hoping. All right, let me clear my drawing here and put us all back here. Couple rules that you want to do when you're doing problems, and I'm just going to do one. All right, why aren't you letting me go forward? Apparently we're still in the annotate mode. So annotate, go away. All right, now I can go ahead. Some rules that you want to put into play when you're solving a problem, and I'll show you how to do that here in a second. If you're tracing around a loop, because the sum of the voltages around a closed loop is equal to 0, you got to remember that if you transfer across a resistor, you transverse across a resistor in the direction of the assumed current. We'll talk about what I mean by assumed current here in a second. That's a voltage drop, right? We said you're going from the high side voltage, where the voltage is higher, to the lower side. And so you make it a negative number. On the other hand, if you happen to be tracing around and you're looking at current that you assumed coming towards you, you're like a salmon swimming upstream, right? You're going from a lower potential to a higher potential, in which case that's a potential rise, and you'll make the potential a positive number. When you go across a battery from the negative to the positive side, it's of course a positive voltage. I'm hoping that's intuitive. If you happen to trace a battery in a loop and you're going from the positive side to the negative side, it becomes a negative number. Of course, Ohm's law applies for all resistors, and in general, in fact, always, and I'll show you why, hopefully, if not today, then on Wednesday, you have to use both a loop rule and a junction rule in order to solve a problem. And I think it was Allison's question All right, why are you not letting me go to the problem I want to do, which is this thing, okay? And I'm going to do this on my tablet, and I want to show you, but I've drawn a circuit, and you notice here, it's a lot like that capacitor circuit. I have a single resistor R1 right here. There used to be another resistor R2 right here, but the first step would be just to combine them in series, and so I'm not going to do that. And then I have two resistors right here that are in parallel. This should look a lot like that problem I did with capacitors at the start of the hour, right? Okay, only the R1 and it's R3 and R4 instead of capacitors in those places. The battery voltage here is given as 3 volts, and our task is going to be to find the current in each resistor. Okay, and so I'm going to jump out of this and get back to my tablet, and so I can draw things, and that'll just take me a second to do. Share that with you. Okay, I got a screen mirror. Okay, we're mirroring a screen, put that away, and hopefully we can see that. It's a practice of mine. I think it's always a good practice. It's time to redraw the circuit. Okay, and so I'm going to do that. Make sure I got the circuit in front of me here so I can draw it correctly. Well, of course I don't. Where'd that piece of paper go? Over here, there it is. All right, so I've got the 3-volt battery. There's my 3-volt battery. And I've got a resistor, and we said that was 1690 ohms. And I guess I called that R1, okay? Then I went to a parallel combination. And one of these was 1,000 ohms. And the other one was 3,000 ohms. Okay, and let's see, we called this, I guess, R3. What did I call it? I think I called it R3 and R4, and I forget the order. Let's go with R3 here and R4. As I said, when I made that diagram, I had an R2, which I've just deleted because it doesn't help the problem. Now, there's a couple ways you can do this problem, and let's look at the clock. I'm kind of running out of time, so I'm just going to do one way. On Wednesday, I'll show you a different way to do the problem, but I want to use Kirchhoff's loop and junction rules. And the one thing is, I'm going to look at that junction right there, and I want to think about the currents, because you can't do a circuit problem like this without assuming you know the direction of currents. And so I'm going to call that I1. And it makes sense that it should be that way. The high side of the battery is right there. That's the high side it should go. There should be a lower potential at that junction. So I'm going to call that I1. Right here, we'll skip over to I3. That's the current going through resistor 3. And of course, there's the current going to resistor 4. Okay. And the first rule for the junction is that I1 has to be equal to I3 plus I4. Everybody okay with that idea? That one's pretty straightforward, and that's why I like to start with it. Let's start tracing loops and employ Kirchhoff's loop rule, okay? The loop rule says, all right, there's a loop right there. Any argument? It's a closed loop, okay? Close the battery up. I'm gonna start right here, and let's pretend it's 0 volts right there. As I go in a clockwise direction around that loop, and it's arbitrary which way you go, okay? I'm gonna see first a plus 3 volts because of the battery. And now this is the high potential side, and this is the low potential side because the current's going from left to right. So it must be a negative number, a negative unknown current 1 times the 1690 ohm resistor. Okay, and then when I get to the resistor I3, the 1,000 ohm resistor, the resistor R3 with current I3 through it, I'm also going from the high side back over to here, the low side, where it's 0 volts where I started, and so minus I3 times, in this case, 1,000 ohms. And I've come back to that X where I started. So that's got to be equal to 0. Okay, one more equation. I'm going to pick another loop. We'll do this one in red. And here's my outer loop right here. And I'm going to use the same rule. Okay, I'm going to go starting from right here again, plus 3 volts, minus I1 times 1690, again, minus because I'm going from the high side of the resistor where the higher potential is to the lower side. Only this time now I'm going clockwise around. I go to I4, so minus I4 times 3,000 ohms is equal to 0, okay? And now what have I got here? This is kind of my answer to the question earlier on what do I have to find? I need to find I1, I2, and I3. Unfortunately, in this problem, the way I do that is I've got to eliminate in an algebraic fashion, like a 9th grade algebra class, I've got to eliminate all my unknowns. And so what you might try here as a strategy is plug in for I1 right there, the sum of I3 and I4, and then some sort of linear combination to eliminate either I3 or I4, solve for that, plug back into one of the other equations, plug back into the initial equation, and you should be able to get the answer. Now, I'm a cheater, so I'm going to show you the shortcut method, okay? And I'm going to stop sharing right here. Anybody used Wolfram Alpha? Yeah, we all have at some point. I love the thing. It takes a lot of the tediousness out of doing physics problems. And so if I can find my web, all right, I guess, you know, I need to escape from that perhaps. Come on, computer. All right, and now hopefully I can find Wolfram Alpha, which I've queued up, and I'll share that with you, hopefully. Come on, where's my share screen? Oh, come on, you silly Macintosh. There it is. Share screen, and I have Wolfram Alpha up, and I'm sharing it with you. And you can see one of the things Wolfram Alpha will do really nicely is right here in the middle. Are you able to see what I'm about to type on? It'll do a system of equations, okay? And so what I'm going to do is I'm going to type in the 3 equations. I'm going to call, as a general piece of advice, I don't like using I's and L's because they wind up looking like 1s. So I'm going to call I1X, I3Y, and I4Z. And so my first equation is that X is equal to Y plus Z, right? And I just did that because now I'll know what the 3 currents are. X is I1, Y is I3, Z is I4. My next equation is that 3 volts minus 1690 times I1, which is X, minus 1000, another 0, times Y, which is I3, has to be equal to 0. And then my third equation is that 3 volts minus 1690 X minus 3000 ohms times Z is equal to 0. Okay, the first equation I typed in was the junction rule. I1 is equal to I3 plus I4. And then I'm doing the 2 loop rules. 3 volts minus 1690 ohms times I1 minus 1000 ohms times I2 is equal to 0. Put a comma in there. And then 3 volts minus 1690 I1 minus 3000 times I4 is equal to 0. Tell Wolfram Alpha to solve it. Give it a second here. And there are my answers. Okay. The current I1 is 3 over 2440. Y, which is I3, is 9 over 9760. And then I3 is a third of that, oddly enough. You can see 3 over 9760. I saw some of you have the TI Inspire. TI Inspire will do the same thing. And if you don't have either of those two, you got to go back to 9th grade algebra, and you got to solve the system of equations as we did. Hey, that's all I got to say. I've gone a full hour here. This takes a little longer to do than it would take in the classroom. We've got a worksheet 21 for today. I'll be hanging around. Do you have other classes? If you have other classes you got to go to, that's fine. The next schedule.
Yeah, I have another class at 10:30, so I'm going to go.
Okay, if you got to go, it's time to do that. Sorry I went long on you. I will be around. Normally I do office hours at 12:30. So I'll be around for questions at office hours from 12:30, and I usually cut it off at 1:30, but I'll keep going through the afternoon. And I'll be on this Zoom channel right here. And so I'll send you out an invitation for that here shortly.
All right, thank you.
Anybody have any questions? All right. In that
Oh,
case,
wait. Can I ask something about worksheet 20?
sure, absolutely. Yeah, and if you've got to go, you can just take off. Go ahead.
Which one is it? I think it's question 3. But I don't have the document in front of me because it's only online.
Okay. Is that the one where if I got problem 3, it's the copper wire connects a car battery to a starting motor? Is that the one we're talking about?
Yeah, does it ask about time in the end?
What is the average time? Yes.
Yeah, that one.
Okay. Let me flip on over to sharing my pen tablet with you again. So new share and iPhone via AirPlay. Share. Okay. Good. Screen mirroring. Screen mirroring. Put that away. And put that away, and I'll clear this all off. And so here's, I guess, what we're talking about. We've got some kind of battery, and then over here we've got the starter motor, which now I'm just going to represent as a resistor, right? And they're asking you about the time between collisions, okay? And if you go back to one of our lessons before the break, we said we have this thing called resistivity. Okay, resistivity is what relates current density to an electric field. And we came up with an equation that said, hey, resistivity is nothing more than the mass of the charge carrier, that's an electron, divided by the charge on the charge carrier squared times this number of electrons per volume, per meter cubed, times the average time between collisions. Now, I can derive that thing again if you want, but that is what the resistivity is. Now, in this particular problem, I think you're given the resistivity for copper, right? You're given that that's 1.69 times 10 to the minus 8th ohm meters. Okay. Let's see, what else are you given? You're given N here. You're given that that's 8.49 times 10 to the 28th, and that's electrons per meter cubed. The things I guess you need to look up are mass and the charge on an electron, and what you're tasked with doing, of course, is solving for that time right there. Tau is a time constant. It's the time between collisions. And so that's all you're doing on this one. The thing to pay attention to, I think, are units, right? This is an ohm meter. That's a mass in kilograms. You got to make sure your units come out right, and they will. Does that answer your question?
Yeah, that's actually really good. And then for the next question, part B, I just got like a really large answer. It doesn't seem right.
Okay. So for which part?
For part B.
Part B.
It is.
It's what number are you getting?
It's 227,272.
Yeah. So I think what I got when I did it, I got something like, well, you're taking what 11.4 amps is I think the current that I got.
Yeah, me too.
And I'm dividing it by 0.5 centimeters squared, and that's a real small number. And so when I converted that to amp per meter squared, which is what you have to do, right? That's the problem. Yeah, I got something like 2.27 times 10 to the 5th amp per meter squared. If you kept it in amp per centimeter squared, it'd be a smaller number. But you know, think about a wire. Are you ever going to have a cross section of a wire that's actually a meter squared? And the answer is no, and that's why it's such a large number. Okay, in reality, wires are much smaller in cross section, but that is the in MKS units, in SI units, the type we use in physics. That's what you have to do. You have to calculate per meter squared. So yeah, it is a very big number.
Okay. That's all.
All right, good. Any others? Anybody else got questions out there?
I have a question for worksheet 18.
Question on worksheet 18? Okay.
Yeah.
Go ahead.
How do you the electric field inside the dielectric? It's letter G.
Yeah, okay. I'm pulling it up here. Letter D. All right, so I guess, let me clear this screen out. Hopefully we agree that the capacitance with no dielectric, people usually subscript that with a 0 for air, okay? is equal to just 3 microfarads, so 3 times 10 to the minus 6 farads, but I would recommend just keeping it as a microfarad here. And we said that if you put a dielectric in a capacitor, the effect is that you take that dielectric constant, I'm drawing it like a K, it's really a Greek kappa, and you multiply by that, okay? And the reason for that is we said that if you take the permittivity of free space, which is something like 8.85 times 10 to the minus 12th, and that's a 12 there, but I'm up in the corner. You get the point here. If you need the permittivity of what's actually there, because it's not free space, it's not air, the permittivity of the material is the dielectric constant times the permittivity of free space. And remember, the equation for a capacitor is the permittivity times the cross-sectional area divided by the separation between the two plates of a capacitor. And what I'm thinking about is something like this. That's the area, and that's D. Well, if it's just air inside there, I use that constant, right? The permittivity of free space. If I put a dielectric in there, some kind of plastic or wax or something, all I do is I multiply by K. And that's why I say take the air value, just multiply by K. So in that case, this means 7 times 3, 21 microfarads is the capacitance once you shove the dielectric in there, okay? And I think if you remember right, I had those 2 plates, and I put a textbook in between them, I put a piece of glass in between them. What else did I put in? I think I had a piece of some kind of plastic or something I shoved in there, and it actually does change the value of the capacitor that we read on the meter. Okay, so that's what we do here. And now if you need the charge then, well, the battery voltage is still 20 volts, so the charge on the capacitor is still CV, as we used over and over again on that first problem today. So it's 21 microfarads, and then it's multiplied by the 20 volts, right? And
Does the voltage also, does it decrease?
No, the voltage is determined by the chemical reaction in the battery cells, right? So we assume it stays constant. Is that your question? I cut you off there, sorry.
Yeah, because I thought on the PowerPoint from the other day, there was like something about like voltage, and I wasn't sure if the fact that it was like disconnected and then reconnected, if that played a role. But like
no. Yeah, no, it doesn't in this particular case. Now, the voltage from the battery is always going to be the same, okay? The one question is there going to be some change in charge? And since I kept this thing, once I reconnected it, we let it come to equilibrium again. We don't worry yet, but on Friday we will, of how the charge, when I reconnect it, goes from the battery to the capacitor. We'll talk more about that on Friday, but for now, we just wait till you come to equilibrium. Once you reconnect the battery voltage stays the same, but you clearly changed by a factor of 7 the capacitance, because you put in a piece of mica in this case. And mica is a very good dielectric, obviously. It gives you the ability to store 7 times as much charge, doesn't it?
Yeah.
And that's the effect. So, and that's why people put things like that in between the plates of capacitors.
So in that case, the other numbers would also just go up by a factor of 7.
I think that's true. So if you're looking at the next one where you go U is equal to 1/2 CV squared, the voltage stays 20 volts, the capacitance went up by a factor of 7, right?
Okay.
Absolutely.
And then for finding electric field.
Yeah, now that's the electric field actually is going to go down, right? Okay, and so whatever you had for the electric field without a dielectric, you divide by the capacitance, or by the dielectric constant.
Okay.
And yeah, that was on one of the PowerPoints, and that is the point of putting a dielectric in. It actually reduces the electric field, and I can show you why that is in a kind of quick sketch. So let's say I had some electric field E0 between the plates, and no capacitor in. No dielectric in between the plates of the capacitor. I put some sort of dielectric. Remember, positive charge goes to this side, negative charge goes to that side, and then you get a little electric field that's going the other way between the positive side of the dielectric material, the atom or the molecule, and the negative side. That subtracts away from the electric field that started this whole thing. And that's why you divide by the dielectric constant. The dielectric constant is always a number bigger than 1. It makes a smaller electric field as the result. But that's the equation you use. And hopefully that makes some sense as to why it goes down.
Mm-hmm.
Okay.
Yep. Thank you.
Wait, for that same area, that problem.
Yep.
What about what's the equation for maximum potential difference? And like, is it different than like when it's maximum? Is there
No,
especially?
okay, where we got that number, so you're looking at H now?
Yeah.
Okay, so I think, don't make it much, you notice that that particular voltage, when I did this calculation for 20 volts, I turned that into an electric field. I got 2 times 10 to the fifth. I think that was actually a number from worksheet 17 too. And then I divided it by 7. I got 28,570. It's either volt per meter or Newton per Coulomb, whichever you like. Okay. And it says in the next part that that mica has a dielectric strength of 150 times 10 to the sixth. Okay. And so that means we're pretty safe, right? That 28,570 volt per meter is much less than the dielectric strength. So it's not going to spark. And I think you've all experienced dielectric strength. When you walk across a rug and then you touch a doorknob, the air actually experiences dielectric breakdown. The electric potential between your finger and the doorknob is big enough that it makes an electric field that's bigger than the dielectric strength of air, and it sparks. Well, that same thing could happen to a piece of mica. And the end result of that is there's a hole in the middle of the mica. I used to do that with plastic. We were trying to develop dielectrics for higher energy capacitors, and we put a greater and greater voltage on it, creating a bigger and bigger electric field until finally the thing failed, and we'd record the voltage and the electric field at which it fails. So that's what we're saying is, okay, we're safe because 28,000 is much less than 150 times 10 to the sixth in electric field. And so then the question is, how big a voltage can I put on this capacitor and still not exceed the electric field maximum value of 150 times 10 to the sixth? You're going to kind of say, oh, is that all you had to do? Because remember that the voltage across the capacitor is just the electric field times the separation between the plates of the capacitor, right? D. And so we're saying, hey, this can only be as big as 150 times 10 to the sixth volts per meter. That's as big as it can be. I think this was 0.1 millimeter, right? 0.1 times 10 to the minus third meters. And so you can figure out what the maximum voltage you can put across. It's a huge number. So our 20 volts is way less than that. We don't have to worry about causing a spark to go from one side to the other because we exceed the dielectric strength of the mica. We're well below it. So that's all you have to do for that one. And so this would, if this becomes the maximum electric field, this would be the maximum voltage you can put from your battery, right? And that's all we're saying.
So all we had to do was multiply
by D.
150 times 10 to the
sixth, yeah.
0.1.
0.1 millimeters. So it's really 0.1 times 10 to the minus third meters, right? And then the meters cancel, and that's what the voltage you can get. That's how much voltage you can put in that battery. If you had a big enough source, you can get up to that voltage and still not break the dielectric. It won't spark across and put a hole in the mica.
Got it.
All right.
Thank you.
You bet. Other questions? All right. Well, then I will end the meeting, and I'll be back for office hours. It'll be my quantum mechanics class finishes at 12:20. And so if I'm a couple minutes late, it's because I'm still finishing up with those guys, and then we'll be available. We'll be available then. And we'll see you tomorrow afternoon. I'll send you an email for the exact time for the 2 labs. I don't know if I'm going to start right at 1:30 and what are our 2 normal start times? 1:30 and 4:30. I may be somewhere in the middle of the lab, and I'm just going to be available for office hours. Instead of a lab tomorrow, you're finishing up worksheets up to 20. And of course, now we just did 21 today as well. So I'll be available to help you with that as well.
So we don't need to be there the whole time tomorrow?
No, tomorrow I'm going to be doing office hours. So
Okay.
if you can do all the worksheets, you don't even have to come. But you have to upload the worksheets to Canvas.
And they're all due like tomorrow by the end of lab?
18, 19, and 20 are due by the end of lab tomorrow. So let's call it the end of the day because some people have the evening lab.
Okay.
All right.
Mhm.
We'll see you all later. Take care now. Recording, we can stop recording now.